Good morning. Welcome to new lecture on modulation, and in today's lecture we will talk about issues of pulse shaping. So, let us revisit the modulator, and we have seen that in a modulator first we get binary sequence, and this binary sequence is converted to weighted train of impulses, and then this weighted train of impulse passes through a filter to get a weighted pulse train. And today we will investigate what is the good value of this PT, the impulse response of this filter, so that we can avoid things like intersymbol interference. So, this lecture will be dedicated to understand the good values of PT. So, in previous lectures we have seen how the choice of PT influence the bandwidth occupancy, and today we will see that if we want to avoid intersymbol interference, you need to use a little bit more bandwidth than the theoretically possible. Okay. And we will also understand in the process what is this intersymbol interference. Okay. So, let us get started, and the first thing that we would see is really a recap of few concepts that we have already seen before. And the first idea that we have seen in one of the lectures in the first week is that this time limited pulses. So, this pulse is a time limited pulse, that means it has a duration only for 10 seconds, and then there is no amplitude in the pulse, right. So, this is a time limited pulse, it confines itself to this duration. Now, if you take a time limited pulse, its spectrum would span from minus infinity to plus infinity. That means the time limited pulses are always band unlimited, right. This we have seen before as well. And we had also seen previously that if you try to band limit a pulse, for example, this spectrum span from minus infinity to plus infinity, if I try to band limit this spectrum, what would happen is that this pulse will spread in time, because band limited pulses are always time unlimited. You cannot have the best of both worlds. So, for example, you cannot have a pulse which is time limited at the same time bandwidth limited, that is not possible. So, if you try to limit in bandwidth, this pulse will spill in time. We can also understand this from Pali-Wiener theorem, as we have already seen that the physically realizable systems has to be causal systems, because only causal systems are physically realizable, right. And why only causal systems are physically realizable? Because causal systems are non-anticipatory systems, and physically realizable systems would be non-anticipatory systems. And then we have also seen that if the system is a causal system, its frequency response should satisfy Pali-Wiener theorem. That means that we have seen, I think in lecture 6, that if the frequency response has to satisfy Pali-Wiener theorem, it simply means that frequency response cannot be 0 for continuous range of frequencies, right. And if the frequency response cannot be 0 for a continuous range of frequency, it simply means that the signal or the system has to be band unlimited, right. So, this is also what we have seen, that physically realizable systems are band unlimited systems. So, this is like the problem, right. So, we get into kind of blind alley, and this blind alley is that these regularity authorities like TRI in India or FCC in USA, they mandate the signals to be band limited signals, right. Why do we want to have band limited signals? So, that your signal should not influence the signal of the another operator, right. So, every operator is given a frequency band to operate, and the signals of those operators should be confined within that frequency band. So, these regularity authorities of India mandates the signal to be band limited, but as soon as you try to make signal band limited, these signals will become time unlimited. So, if I want to see the signals in time domain, they will be time unlimited. And if they become time unlimited, what would happen? This pulse will interfere with this pulse, and this causes what is known as intersymbol interference. Okay. And we have to deal with this issue of intersymbol interference. So, in this lecture today we will see and identify the pulse shapes that are approximately time limited and band limited, so that these ISI effects or intersymbol interference effects are mitigated. Okay. So, in short, what we have said so far is that because of regulations, the signals have to be band limited, and as soon as you want to make them band limited or approximately band limited, they also spill in time, and when they spill in time, they begin to interfere with other pulses and causing what is known as intersymbol interference. So, to understand this issue clearly, let us look at the communication system. So, we have here in the modulator, and we have the bit stream. Bit stream is converted to samples or a weighted impulse train, and then you pass it through a filter. Also at this point we have frequency up converter, but we do not want to go to the passband domain, because this baseband signal has the complete information, right. So, we have already seen what happens when you go from baseband to passband domain. We are not having this frequency up converter or frequency down converter at this point, because those issues have been addressed separately, right. Here we just want to focus on baseband communication, right. So, okay. So, that is a modulator, we have seen it before, and we have also seen the typical design of a receiver. Receiver has a filter with an impulse response RT, followed by a sampler which is sampling at an integer multiples of t. Okay. So, this is typically the design of a communication system, and first we are assuming all these filters and the channel and this filter to be linear time invariant system, and you must have seen from the course in signals and systems that if you have 3 LTI systems with impulse response PT, HT and RT, these 3 systems can be converted into one system which has got an impulse response formed by the convolution of these 3 impulse responses. Okay. So, namely GT, which is the impulse response of the equivalent system, is simply PT convolution HT convolution RT. Okay. So, if the systems are linear time invariant systems, you can replace these 3 systems with one linear time invariant system which has got an impulse response, the convolution of the impulse responses of these 3 systems. Okay. So, here we are using the same idea that we have these 3 systems. This filter has got an impulse response of PT, channel also we are assuming to be linear time invariant system, and then we have a filter with an impulse response of RT at the receiver. These 3 systems can be replaced by one filter which has got an impulse response PT convolution HT convolution RT. So, this is typically the communication system. Then the question that we are asking is, if let us say at the input of this filter we have got a signal AT, where AT is given by this. So, it is nothing but it is a weighted impulse train. At the output of the filter, this filter, let us assume that we have a signal QT, where QT is given by input convolution GT. So, input is this is the input, convolution with GT. So, this is the output of this filter, and we also assume that some noise has added in at the output. So, we have the signal convolution with impulse response of the filter plus some noise addition, right. We have seen that noise is additive. So, it simply adds at the receiver. Now, you know that delta t minus kt convolution with gt is simply gt minus kt. Okay. So, this is convolved with this is not a function of time. So, a k's are constant with respect to time. So, this simply becomes a k times g t minus k t summation for all possible values of k plus n t. And the question that we want to ask is, if I sample this output, let us say at I t. So, if we sample this q t at I t, we get q of I t, and we want this q of I t to be same as A I. Why is this so? Because at I t time instance, we are transmitting A I, the symbol with the value of A I, and at the receiver what we want to receive is A I faithfully. Okay. So, let me draw this. So, let us say at the input of this filter A t is nothing but it is a weighted impulse train. So, let us say 0 t, 2 t, and let us say I t, and it has got the weight A 0, A 1, A 2 and A I. So, at I t time instance, we are sending an impulse with the weight A I, and at the output of the filter G t, after sampler, what we want to receive is A I faithfully, right. That is the job of a communication system. Whatever you are transmitting at the output of a filter and the sampler, you want to receive faithfully that. Okay. So, that is the question that we are asking. We want that q I t should be same as A I, and we are asking the question that for what g t, for what impulse response this q I t is same as A I. And let us see this. So, we have already said that q t is A k times g t minus k t summation for all values of k, and then there is some noise addition. Now, we want to sample this output at time instances with integer multiples of t. So, I get q I t is A k. So, this t is replaced with I t, and this t is also replaced with I t. So, this is the q I t, this is the values of the samples of this output q t. If we look this carefully, let me first do it separately. So, what we are saying is q I t is summation A k g I t minus k t plus n t. K takes in all values from minus infinity to plus infinity. This is also I t. Now, let me assume that I is same as k, or k is same as I. So, that is A k times g of 0, and I can collect all other terms other than when k is not same as I. So, this is q I t. So, this summation contains all terms going from minus infinity to plus infinity. What I am doing is I am just pulling out the term corresponding to the situation when k is same as I. So, that term is A k times g of 0, and all other terms are contained in the summation except when k is same as I, and then also we have n I t. So, this is what we have. So, q I t is represented in this term plus this term and noise. So, what we wanted is QIT should be same as AI. So, this is the information that we want, and this is intersymbol interference. So, this is intersymbol interference. And this term corresponds to the noise, and we want that this intersymbol interference to be 0. So, that is the objective, because what we want is QIT should be just same as AI, nothing else. Okay. There should be no contribution from this summation. This summation corresponds to intersymbol interference. So, what is the question that is running on? The question is, what is the value of GT? So, what is the value of GT for which QIT is same as AI? So, that is the question that we are asking. But we will ask this question making two assumptions. First assumption that we make now is that noise is 0. We do not want to study at this moment the impact of noise. We assume that noise is 0. So, that we just handle intersymbol interference at this moment. Okay. And this will be the case when the signal to noise ratio is pretty large, and signal to noise ratio is large in channels like telephone channels. So, this is fairly a reasonable assumption to make. And if signal to noise ratio is pretty large, that means this noise power is small, or that simply means that noise can be ignored. So, in the absence of noise, most errors happens because of this intersymbol interference, and that is what we want to focus at this moment. The second thing that we are assuming is that this filter GT is a linear time invariant filter. And before we have assumed that this PT, HT and RT, all these are linear time invariant systems. Can we have a filter which is not linear time invariant, or can we have a system which is a non-linear system? Could we have used the systems replacing these filters with impulse response of PT and the impulse response of RT and the channel with an impulse response of HT with non-linear systems? Can then we not get QIT same as AI? Why we are restricting ourselves to linear time invariant systems only? The answer is that if we assume non-linear systems are not optimal in the presence of noise. Okay. So, when we are restricting ourselves to linear systems, actually we are not losing out anything, right. Linear systems are well behaved even in the presence of noise, and this is a good assumption to make. First, it makes analysis simple, and second is linear systems are well behaved and optimal in the presence of noise. And that is why we are asking this question, that for what GT QIT is same as AI, by assuming all systems to be linear time invariant systems only. Okay. So, these are the two assumptions that we have made. We have made that all systems, the channel is LTI system, the receiver filter is LTI system, the transmitter filter is an LTI system, and second assumption that we have made is that the noise is ignorable. Okay. So, signal to noise ratio is pretty large. Okay. So, let us go back and look at this question again. So, we have been asking this question several times. So, we are saying QIT is this. So, now we do not have any component corresponding to noise, and if you ask for what GT QIT is same as AI, answer is pretty simple if you look at this. What we want G of 0 to be, G of 0 should be 1, right. That means GT should be 1 for t equals to 0, and what we want here? We want that GT should be 0 at t equals to KT. So, if GT is 0 for t equals to KT, there will be no contribution from this term, and intersymbol interference will be 0. So, if I use a filter whose impulse response satisfies these two conditions, then what we can see is that the intersymbol interference will be 0. Okay. So, What are the examples of GT? A sinc function. So, for example, we know that a sinc function sinc t by t is a function which has at t equals to 0 a value of 1 and at all integer multiples of t it has 0. So, sinc function is a function that satisfies Nyquist criteria, and this is in fact the Nyquist criteria even though we have not mentioned it. So, this is Nyquist criteria that GT should be 1 for t equals to 0 and for t equals to kt GT should be 0, and if you have a function which satisfies this, then intersymbol interference is 0, and this function is known as Nyquist pulse at rate 1 by t. Okay. And sinc function is an example of the Nyquist pulse because it satisfies this condition. So, it is easy. But what is the problem with this pulse? The problem with the sinc pulse is that the sinc pulse extends from minus infinity to plus infinity, and we have seen that this sinc pulse sinc t by t, which can be approximated as some sine by t. So, we are not writing on the exact values, the only thing that we need to appreciate is that sinc t by t translates to some constant times sine of something divided by t. This is an oscillatory function, it goes up and down, and so for large values of t this function decays as 1 by t, and this is a slow decay, and because of the slow decay in practical situations this is not a good function to use even though theoretically it is fine. So, what we are saying is the sinc function decays as 1 by t, and thus for practical applications this is not a nice function to use, because what would happen is in practical situations, let us say we are using a sinc pulse. So, one sinc pulse is like this, and let us use another. So, this is p of t, and then let us draw p of t minus t, which would be something like this. Let me draw one more. Something like this. Something like this. So, this is Pt, this is Pt minus t, this is Pt minus 2t, and where we are sampling? We are sampling at these instances. So, we are sampling here, we are sampling here, and we are sampling here, and so on and so forth. So, this is 0, t, 2t, and so on and so forth. So, now what you see is that when you sample this, you just have contribution from Pt. The contribution from Pt minus t and Pt minus 2t is 0. When you are sampling at t, you just have contribution from Pt minus t, but contribution from Pt and Pt minus 2t is 0, and hence this looks like it is avoiding intersymbol interference. But what happens in practice is that your clock does not sample exactly at the duration of t seconds, right. This pulse is created at the transmitter, this clock is at the receiver. So, there might be a mismatch between this pulse duration of t and the sampling duration of t, because this clock is produced at the receiver. Moreover, for the same clock there is always some jitter. So, sampling instances do not always perfectly happen at the duration of t. So, there might be some jitter in the clock, and sometimes you may sample here, sometimes you may sample here. And once there is a clock jitter, what happens if you sample at this time instance, you begin to have contribution from this pulse and many other pulses. And in the presence of this clock jitter, this might become pretty large value, and hence it will create an error. So, what we are saying is, if you can have a clock which can perfectly sample at a duration of t seconds, and this duration of t seconds is matched to the duration of the sync pulses produced by the modulator, then there is no problem, right. But in practice what happens is that there is clock jitter. So, the sampling time instances are not perfect, they do not always happen at integer multiples of t, but there is some drift, sometimes it happens earlier, sometimes it happens later. And once there is a clock jitter, whenever you sample these pulses, there might be contributions from all pulses, and this contribution might sum up and may become a pretty large number, and it might create an error. Okay. So, that is the problem with the sync pulse. So, what we are saying is, let us go back. So, because the sync pulse decays too slowly, it has a decay of 1 by t. When you take into account the sampling time errors, let us say if instead of sampling at t, which is fine, you begin to sample at t plus delta, where delta corresponds to the jitter in the clock, then you begin to collect samples from all pulses, then you begin to have contributions from all pulses, and this contribution might add up and may become unbounded. In fact, it can be shown that the worst case error for a signal which decays as 1 by t is given by this series. So, if your pulse decays as 1 by t, this is the contribution from all other pulses, and this series diverges, and thus the sampling errors can be unbounded. So, what we want is, we want the signal to decay faster, we want it to decay with 1 by t square, because when it decays as 1 by t square, you can see that the worst case error due to other pulses has a contribution proportional to this series, and this series converges, and thus we want pulses which decays faster than the sync pulse. So, sync pulse, though theoretically is good, practically it will have issues, right. So, practically what we want is, we want the pulses that decay faster than 1 by t. So, we want them to decay with 1 by t square or 1 by t cube and so on and so forth. And you can show that easily, that the sampling error when you have a pulse with this decay is given by this series, and this series converges. The sampling error for the pulses which has this kind of decay is given by this series, and this series also converges. So, we want pulses that decay like this or like this. In terms of frequency response, what we want? So, you can see also from basic course in signals and systems that if you have a frequency spectrum like this, it is a discontinuous spectrum, whenever you have these discontinuities, the pulse in time domain decays as 1 by t. If you have first derivative discontinuity, so if you differentiate this signal, you end up with signal like this, is not it. So, when you have a first derivative discontinuity or slope discontinuity in the spectrum, this translates in the time domain to a pulse or to a signal which decays as 1 by t square. If you have a frequency response which has second derivative discontinuity, so if you differentiate it twice, then you get to a signal like this. Then in time domain, this will correspond to a pulse which decays by 1 by t cube. So, you can understand the examples of good pulse from both time domain where you just have to see whether the decay is proportional to 1 by t square or 1 by t cube or higher. If you want to understand this good pulses in terms of frequency response, you can also understand this by ensuring that the frequency response should have either first derivative discontinuity or should have second derivative discontinuity. It should not be discontinuous function. Discontinuous function is bad. Okay. So, we want the pulses which satisfies either this condition or even better conditions in terms of intersymbol interference and reducing sampling errors, and that is it should have second derivative discontinuity. Okay. So, now we have to determine the frequency response of the good pulse. So, to determine GF corresponding to good Nyquist pulses, we again make use of this impulse train. We take in this impulse train has the impulses which are separated by a duration of t seconds, where t corresponds to the rate at which you are producing those AKs. So, if you see, we had this AT which is AK PT minus delta t minus KT. So, what is this? So, you have impulses which were separated by a duration of t seconds and they carry the weights A0, A1, A2 and so on and so forth. And what are these A0s, A1 and A2? If we are in the regime of digital communication, these are quantized real numbers and actually these are symbols. So, we had a symbol rate Rs which is 1 by t. So, at every t seconds your modulator spits out a symbol. So, symbol rate is 1 by t and this A0, A1 and A2s are symbols, quantized real numbers. So, this t is the same t at which we were producing symbols, and we know that what is GT? The two conditions for GT that must be satisfied is it should be 1 at 0, and for all this timing instances which corresponds to integer multiples of t, GT should be 0. So, if I multiply this impulse train with GT, what I end up with is an impulse. So, this is what I am saying, GT multiplied with an impulse train is nothing but an impulse. Now, we know that multiplication in time domain is convolution in frequency domain. So, if GT has a frequency response GF, what is the frequency response of this impulse train? Is an impulse train given by this relationship. So, this you must know from before, and this we have also derived in one of the lectures. If you have this impulse train, its Fourier transform is nothing but delta f minus k 1 by t divided by t, where k goes from minus infinity to infinity. So, an impulse train has frequency response which is also an impulse train. This impulse train is also known as picket fence, right. So, because you have these pickets are soldiers. So, these impulses looks like soldiers, pickets. So, we have this impulse train which is also known as picket fence, has a Fourier transform which is also a picket fence. So, leisurely we say that picket fence has Fourier transform which is picket fence. Anyways, so we have an impulse train, the Fourier transform of this impulse train is also an impulse train. Of course, it has a frequency of 1 by t and then there is an extra factor of t in here, and what is the Fourier transform of delta t is 1. So, what we can say is GF convolution, this thing should be same as the Fourier transform of delta t, which is 1, and we know that GF convolution with impulse gives us this. So, I have taken t to this side. So, we have seen this several times, that if you take a signal, convolve this with an impulse, you just get the same signal, but it is shifted to the point where impulse has an effect. So, delta is simply replaced by g, that is it. That is the effect of convolution of a signal with an impulse. And then I write 1 by t as R s, where R s is the symbol rate. So, we get this condition. So, the frequency response of a Nyquist pulse must satisfy this condition. So, let us look at this. What does this mean? This simply means that, so let me write this. So, if I have G f minus k R s is t, k going from minus infinity to plus infinity, it simply means that if I have a G f, let's assume some G f. So, let us say G f, and then I have G f minus R s plus G f minus 2 R s, and so on and so forth, all these terms. So, if this is G f minus R s would be, let us say this, G f minus 2 R s, let us say would be this. So, let us say this is G f minus R s, this is G f minus 2 R s, and so on and so forth. So, you have a spectrum and you have various shifted spectrums, where the spectrums are shifted at R s, 2 R s, 3 R s, 4 R s, and so on and so forth, and you add up all these spectrums, then what you should get is some constant. So, that is the Nyquist criteria in frequency domain. So, if G f is the frequency response of the Nyquist pulse, you take that spectrum, you shift this spectrum at integer multiple of sample rates, then you sum up all these spectrums, what you should get is a flat constant. So, that is this picture is saying, we have this G f. So, this is G f minus R s, and so on and so forth, G f minus 2 R s. So, we have this main spectrum, we shift this by R s, this by 2 R s, and so on and so forth. Then I add all of them, I should get a constant. So, t. In this case, for this diagram, what I have assumed is R s is 1 and t is also 1. Okay. So, that is the interpretation of this equation, and this should help me in identifying what are possible solutions for this G f. So, let us start by making some assumptions. The first assumption that we make is G t is real and symmetric. That would imply that G f is also real and symmetric. If a time domain signal is real and symmetric, its frequency spectrum is also real and symmetric. And if we want to look at this equation for frequencies between 0 and R s, what happens? So, let us make a diagram for this. So, if we have G f, which let us assume is confined between minus R s and plus R s, and we take a shifted version of that, like this. Let us assume that this is G f minus 2 R s, this is 2 R s. So, sorry, G f minus R s, and let us then consider third spectrum, which is G f minus 2 R s, then what you can see is that GF minus 2 RS and the spectrum which are shifted beyond this 2 RS would have no impact in summation for frequency range between 0 and RS, because they are shifted at 2 RS, and if GF is limited between minus RS and RS, GF minus 2 RS and the spectrum beyond that, the spectrum shifted beyond 2 RS would have no impact in the summation. So, between this frequency range, that means the frequency between 0 and RS, I will have the impact of GF and GF minus RS. Let us now assume that f is x plus RS by 2. So, there is a change of variable, and I assume that mod of x is less than RS by 2. So, that this is satisfied. So, when I assume that f is x plus RS by 2, I simply substitute that in here and I get this, and then what we can do is we can just write this as g of minus RS by 2 minus x. So, from this we have got this equation, and because GF is symmetric, g of minus f is same as g of f. So, this is nothing but this. So, from this we can get g of RS by 2 plus x is t minus g of RS by 2 minus x. And this condition is known as band edge symmetry condition or vestigial symmetry condition. That means the spectrum of the Nyquist pulse must satisfy this band edge symmetry or vestigial symmetry, by which I mean that this should be satisfied. And the first thing that you can understand is, just let us assume x to be 0. If x is 0, then g of RS by 2 should be same as t minus g of RS by 2. From this we get g of RS by 2 should be same as t by 2. So, that is what we have got. So, let us assume that this is t. So, this is what we are plotting is GF. So, let us assume that this is t. So, on this axis I have f. So, at frequency corresponding to RS by 2, I should have a value of t by 2. So, this value is t by 2, and as I shift x from this point, this distance is x. So, let us assume that the value of g RS by 2 plus x is y. So, this is y. So, what should be the value of g RS by 2 minus x? Let us work this out. So, g RS by 2 minus x should be nothing but t minus g RS by 2 plus x, and this we have said is y. So, g RS by 2 minus x should be t minus y. So, this value should be t minus y, and this total duration is t, right. So, this is t. So, what should be this? This should be y, and this is the idea behind vestigial symmetry. If you move x from the center frequency, so center frequency I mean RS by 2, where the value is exactly half of this total value. So, if you move x to this side and x to this side, if this value is y, this value is also y. So, GF should have a spectrum which should have this band edge symmetry. Okay. So, this is the solution following from very simple ideas, right. And what is the idea? Idea is simply that GT should be a function which should be 1 at t equals to 0 and it should be 0 at the sampling instances which are integer multiples of t. Okay, so, we now know what or how should the spectrum of Nyquist pulse should look like. There are 1-2 small points that are remaining about this spectrum GF. Let us look at this. So, one thing is, let us assume that GF is restricted to frequencies less than Rs by 2. Okay. So, let me first write that equation GF plus GF minus Rs should be constant. Again we are looking only at the frequencies between 0 and Rs. So, if let us assume that GF, let me make one scale. So, let us assume 0 here and Rs is here, two Rs is here, minus Rs and minus 2 Rs. So, this is Rs by 2. So, let us assume that I have a GF which is like this, and now this is my GF, and so I also have to have GF minus Rs, which would be this. So, this is GF minus Rs, and if I add these two things up, what would I get? They are not overlapping. So, what I will get is exactly this, and this is not a constant. And so, what we learn from here is, if GF is restricted to frequencies less than Rs by 2, then this condition can never be satisfied. So, this can only be satisfied if GF has the support at least greater than Rs by 2. With support I mean one sided support. So, GF should have one sided support at least greater than Rs by 2, then only this condition can be satisfied. So, this condition will not be satisfied if one sided support of GF is less than Rs by 2. Okay. So, this has to be kept in mind. So, from this we have got very important idea that minimum bandwidth of GF is Rs by 2. This is absolute minimum bandwidth, because if bandwidth is less than Rs by 2, then you can never satisfy Nyquist criteria. And so, we have looked into the sync pulse GT, sync T by T. What is the spectrum of this sync pulse? The spectrum of this sync pulse is a rect, and where does you have a null in here? At 1 by 2 t. So, what is the one sided bandwidth of this signal? The one sided bandwidth of this signal is 1 by 2 t, and what is 1 by t? It is Rs. So, the bandwidth is Rs by 2. So, if I choose the sync pulse as the Nyquist pulse, then the sync pulse translates to a rectangular spectrum, and the one sided bandwidth of this function is Rs by 2. Thus, if I choose the sync pulse as the Nyquist pulse, then what I am doing is I am getting an advantage that this pulse requires minimum bandwidth and it satisfies Nyquist criteria to avoid intersymbol interference. But the problem would be that this spectrum, as we have seen, is a discontinuous spectrum, and when you take into account the practical situations of jitter in sampling clock and so on and so forth, the sampling errors might become unbounded, and that is the reason why we want to avoid this pulse. However, this pulse is best in terms of the bandwidth requirement that it offers. And so, the idea is I need to use the pulses which maybe require little bit more bandwidth than RS by 2, but it offers me a smooth decay from t to 0. Okay. So, if I let us say have a sync pulse, so this is sync. If I have sync pulse and if it has to satisfy Nyquist criteria, which is this, then you see that this would have a spectrum. So, this will be GF 0 RS by 2, and you will have GF, so GF minus RS, and this should be T, and because these are non overlapping, so this amplitude should also be T. So, the spectrum, so GF should be spectrum like this, which is T between 0 to RS by 2, and then this is 0. Okay. So, this satisfies band edge symmetry, this also satisfies this condition. The only problem it has is the sharp discontinuity. So, to avoid sharp discontinuity, what we want to do is to have little bit more bandwidth. So, we have seen that for RS by 2, my value should be T by 2, and then it should have some band edge symmetry. So, I can have a some pulse like this. So, what is this pulse doing in? It is having little bit larger bandwidth than RS by 2, and assuming that it is satisfying band edge symmetry. If it satisfies band edge symmetry, then it would satisfy this condition. And if this decrease from T to 0 is smooth, this might be a good example of the spectrum of the Nyquist pulse. So, we will see what are the good examples of the spectrum of the Nyquist pulse, but at this moment I am trying to highlight two important ideas. One important idea is that to satisfy Nyquist criteria, the minimum bandwidth that GF should have is RS by 2. Second thing that we have understood is, if you want to have minimum bandwidth of RS by 2, the solution is the sync pulse, but sync pulse has a discontinuous spectrum, and there becomes all troubles related to sampling errors and so on and so forth. So, what you would like to do is to spend little bit more on bandwidth. So, you want to have bandwidth little bit more than RS by 2, and using this little more bandwidth, what you would like to do is to allow your spectrum to make a smooth transition from T to 0, because the smooth transition would allow it to have sampling errors bounded, and as long as it satisfies band edge symmetry and as long as it satisfies Nyquist criteria, then the intersymbol interference can be avoided. Okay. So, for all this discussion, what we have assumed is that GF is real and symmetric. The question that we ask is, what if GF is complex? Do we get any more benefit? If GF is complex, then instead of this condition, it should satisfy this condition. You can break this G into two parts, real parts and imaginary part, and this should be T. So, from this we get that this should be satisfied and this condition should be satisfied. Now, by having the imaginary part, you do not have any different condition than the condition that we had before. So, the real part should satisfy the same Nyquist criteria as it had to satisfy before, and thus by having imaginary part we do not improve in facilitating a smoother transition from T to 0. So, this does not help us in any way in making the spectrum to move smoothly from T to 0, and thus this is redundant, and we might face some more energy by having an imaginary part. So, what I am trying to point out is, by having GF to be complex, we are just wasting energy in having some imaginary part, and having an imaginary part is helping us in no way in having a spectrum which goes more smoothly from T to 0. So, thus we restrict GF to be real. Okay. Then now next we want to develop is some examples of GF that are used in practice, and to understand them we have to understand this Roloff factor. So, the Roloff factor is defined in terms of this ratio of excess bandwidth divided by Rs by 2. Remember, Rs by 2 is the minimum required bandwidth. So, we have said that this is minimum what we require. So, if I look at GF, suppose GF is like this, and we know that this must be Rs by 2. At this point this should be T by 2, this is T, and so this requires little bit more bandwidth. So, this part, this is referred to as excess bandwidth. So, Roloff factor is nothing but it is the ratio of this excess bandwidth divided by theoretical minimum bandwidth, and we confine this Roloff factor to be between 0 and 1. So, you do not want to have lot of excess bandwidth, because then it will lead to bandwidth wastage. So, what we want to do is we try to keep excess bandwidth at most as Rs by 2. So, the theoretical bandwidth then would be required would be Rs by 2 plus excess bandwidth, which is Rx, and Rx is nothing but it is R times Rs by 2. So, the bandwidth requirement is Rs by 2 times 1 plus R, where R is the required Roloff factor. So, let us look at the examples of GF that are used in practice. So, here we have example of raised cosine pulse. A raised cosine pulse has such an spectrum. Okay. So, what it simply says is that what are the key points? So, we have 0, Rs by 2, and we want to restrict ourselves to Rs. Okay. Similarly, you will have minus Rs by 2 and minus Rs. Now, what we see is that here we should have a value of T, and at Rs by 2 I should have a value of T by 2. Okay. So, this is to satisfy Nyquist criteria, and this we have already seen before. Now, what should happen is you should have to satisfy band edge symmetry, which for the raised cosine pulse we choose this function as a cos square function. The exact expression is given in here, we are not worrying about that, but in general this has to be some cos square function, okay. And this would take some excess bandwidth, and this point is Rs by 2 1 plus R. This point similarly is Rs by 2 1 minus R. So, this is how the spectrum of a raised cosine pulse will look like. It should be constant for mod of frequencies less than Rs by 2 1 minus R. For frequencies between this and this, it should be given by cos square function. This is a cos square function, and for frequencies greater than this, it should be 0, right. And here I have the exact spectrum drawn in for you for two Roloff factors. Of course, R equals to 0 is the frequency response of the sync pulse, right, and for R equals to 0.5 some excess bandwidth is incurred and the spectrum becomes continuous, right. If I take the inverse Fourier transform of this pulse, we get this pulse, and if you see carefully, this decays by 1 by t. So, I have cos pi r t by t. So, this is basically an oscillatory term, it does not decay with t, and this term for large values of t decays as 1 by t square. So, g t decays approximately as 1 by t cube, and this also is clear from the spectrum, because the spectrum has second derivative discontinuity, okay. And this is a very popular example of the pulse that is used. It goes by the name of raised cosine pulse. I have the picture corresponding to the frequency response of various Roloff factors. So, this one is R equals to 0, 0.4 and so on and so forth. The basic idea is simple: as Roloff factor increases, excess bandwidth requirement increases, but in time domain signal becomes more and more confined, right. For example, at R equals to 1, I have a signal like this, okay. It becomes more and more time limited as Roloff factor increases. It would be a good idea for you to plot these frequency response and impulse response yourself by changing the value of R. Finally, let us come to the last point. Here we have talked everything with respect to GT, where GT has an impulse response obtained by the convolution of impulse response of this filter, channel and this filter. Now, what we have done is we have introduced one more block which goes by the name of equalization filter, and we are saying that this equalization filter has an impulse response h dash t, and this equalization filter is to inverse the effects caused by channel. So, if channel has an impulse response of h t, if I use a filter with an impulse response of h dash t, and if I choose this equalization filter impulse response such that h t convolution h dash t is delta t, then you know that this channel impact would be negated by this equalization filter. Because now what would happen is G t would be P t convolution H t convolution H dash t convolution R t, and this is delta t. P t convolution delta t is nothing but P t convolution of R t, convolution with R t. So, G t is nothing but P t convolution with R t. So, channel effects are negated. So, in the presence of equalization filter, G t is given by P t convolution with R t. And how should we select this R t? Remember that the R t is the impulse response of the meshed filter. So, let us see what we have seen about this meshed filter. We have seen about this meshed filter in lecture number 4. So, we know that if we have to receive a signal ST which is expressed in terms of orthonormal functions phi 1 t, phi 2 t and phi k t, then the job of the receiver is to extract the coefficient of this signal along these orthonormal functions. And the way we can extract the coefficients of this signal along this orthonormal function is to use what is known as a meshed filter. Okay. And meshed filter simply has an impulse response which is meshed to one of this orthonormal function. So, namely if this mesh filter extracts the coefficient A1 of the signal ST along phi 1 t, then the impulse response of this mesh filter is phi 1 t minus t, and then there is a sampler which samples the output at t. Okay. And similarly, you can have other mesh filters and you can extract the coefficients A1, A2 and AK. We have seen all of this in lecture number 4. So, we have also seen that if these phi 1 t, phi 2 t and phi k t are complex functions, then the impulse response of the mesh filter also need to have this conjugation, because the job of a mesh filter is simply to calculate the inner product. So, it would be calculating the inner product of ST with this orthonormal function phi 1 t, and you can prove it yourself that if this receiver has to carry out this inner product operation, then the impulse response of this filter should have a conjugation, okay, if these functions are complex functions. All right. Now, let us see something else. Here we have assumed that d is some constant and the sampler also needs to sample at this time t. All right. We can assume the value of t also to be 0. So, we can have the impulse response which is phi 1 minus t conjugate, and you can sample at time instance 0. Of course, this will create causality and realizability issues which we have seen in lecture number 4, but let us forget these causalities and realizability issues for simplification, and let us simply assume that the impulse response of the meshed filter is simply phi 1 minus t conjugate. And what we will get is the coefficient A1, right, but the job of a communication system is to continuously receive signals, right. It would not stop by just getting this signal A1. So, in general the signal does not just transmit one coefficient, it transmits a series of coefficients. So, it transmits A1, A2, A3 and so on and so forth, and it transmits these coefficients or these symbols at integer multiples of t. All right. So, let us see what would be the design of a meshed filter in that case when the meshed filter should receive these symbols A1, A2 and A3. So, to understand that, let us assume that I have a signal ST, and first I pass the signal ST through a filter phi 1 t, and then let us assume that I have a meshed filter which has this impulse response, and then I am sampling at integer multiples of t, and let us assume that I have got some output yit. So, Bt, which is the output at this filter, is simply ak phi 1 t minus kt, and why is this so? Because this Bt is nothing but St convolution with phi 1 t, and we have seen this several times that in that case Bt will be simply this function. This output at this place would be Bt convolution with phi 1 minus t conjugate, and let us solve this out. So, then we can say yt is this function. So, what we have just done is we have carried out the convolution operation. Now, when I have to find the output at I t time instances, I just have to substitute t as I t. So, substituting t as I t, we get this. If this phi 1 t minus k t is an orthonormal set for k belonging to a set of integer, then I can easily appreciate that this would be 0 if k is not same as I, because it is an orthonormal set, and if k is same as I, then this will be 1. Okay. In that case, if this phi 1 t minus k t are orthonormal set for k belonging to set of integer, then y I t is simply a I. Okay. So, this summation would have contribution only when this is 1, and this will be 1 when k will be same as I. In that case, a k will have contribution only for a I, and rest terms will go to 0 because of this function. So, y I t will be a I. So, what we learn from this is that if you want to make a receiver which is receiving the sequences continuously, the sequences were transmitted at integer multiples of t, then the matched filter should look like this, and here we are ignoring any causality and realizability issues. Okay. So, in short, we can simply assume the matched filter response as phi 1 minus t conjugate, followed by a sampler which is sampling at I t time instances, and this matched filter will give us sequences which are transmitted at integer multiples of t. Okay. So, in short, I can say that the impulse response of a matched filter is phi conjugate of minus t. Okay. So, this is what we are saying in here. So, I am having a matched filter's impulse response is matched to the filter's impulse response. If I take the Fourier transform of this, from this I get R f is p conjugate of f using the properties of signals and transforms. Now, what is G f? G f is nothing but P f times R f, and R f is p conjugate f. So, G f is P f times p conjugate of f, and this is mod of P f square. So, from this we get mod of P f should be square root of G f, and what is G f? It is a raised cosine filter that we have seen, and so the mod of P f should be square root of raised cosine. So, the filter that you have to use at the transmitter should have an impulse response which is a square root raised cosine, and that is important. Okay. So, whatever we discussed before was for G t and G f. G f has to be raised cosine, but the P f or mod P f has to be a square root of raised cosine. So, this goes with an abbreviation of SRRC. So, what we know is mod of P f should be square root of G f, and P f in general is square root of G f into some angle. So, we can choose this theta f ourselves, and there is no restriction, there is only restriction on what should be the amplitude of this P f. So, if you choose this P f with this angle, you have to choose R f. So, R f, because R f is P f conjugate. So, then this R f is this theta. Okay. And one last issue that we have to see is that this G t is nothing but it is P t convolution with R t, and we are assuming that channel has been compensated and has been accounted for by using this equalization filter. And we have seen that R t is P minus t conjugate. In that case, G t is P t convolution with P minus t conjugate, and just writing out this convolution operation, we get G t is this function. Okay. So, simply replacing this t by t minus tau. So, p of minus t conjugate will become p conjugate minus t plus tau, all right. Then putting this t as kt, we get g of kt is, so we have to substitute t as kt, we get this. Now, what should be this g of kt? We know that g of kt should be 1 if k is 0, and if k is not 0, then this should be 0. This is from the Nyquist criteria to avoid intersymbol interference, and we have seen this before. So, from this we get this should be 1 for k equals to 0, and it should be 0 for k not equals to 0. And thus, we are saying that this pt minus kt should be an orthonormal set for k belonging to a set of integer. So, what we say is, if we have pt which satisfies Nyquist criteria, then pt minus kt should be an orthonormal set. You can also conversely prove that any orthonormal set will also satisfy Nyquist criteria. Okay. So, we know that we can easily generate several Nyquist pulses, and this is an easy way also to generate several orthonormal sets. All right. So, in this lecture today, we have clearly understood how should we choose this pt and this RT as well, this matched filter response, to avoid intersymbol interference. Of course, we have not considered noise at this moment, but later when we will see noise, we will also see that this is an optimal thing to do even in the presence of noise. And what we have identified is that this filter response should be belonging to raised cosine family, where you end up with different functions for different values of roll of factor. As you increase roll of factor, you span little bit more bandwidth than the minimum required bandwidth, and the advantage of doing that is to make the frequency spectrum having a smooth transition from t to 0, and we have seen that we can have the spectrum which has the second derivative discontinuity, and because of this second derivative discontinuity, the time domain equivalent of that spectrum would decay with 1 by t cube, and that will allow the sampling errors to remain bounded, and this is important from practical point of view. So, in the next coming lectures, what we will do is we will look at some examples of modulation schemes. Particularly, we will start by looking at pulse amplitude modulation and quadrature amplitude modulation, and then we will define bandwidth efficiency and other parameters for those modulation schemes. Thank you.